All right, so we've just done the analysis for a recursive algorithm, for the Tower of Hanoi algorithm. Now let's do a non-recursive algorithm, and we'll use this algorithm to prompt questions of best case, worst case, and then a little bit of average case as we move forward. All right, so here's the basic algorithm we're going to use is called the unique elements algorithm. And so the problem we want to solve is we want to look for repetitions in an array. So we want to find repetitions in an array. And the way we'll do that is we'll ask the unique elements question. So unique elements asks, given an array, are all the elements in the array unique? Or you could also use the word distinct. Is every element in the array different from every other element in the array? So the unique elements problem is it's a Boolean question, right? And the question is, are the input arrays, or are all elements in the array A, in A, 0 to n minus 1, unique? Okay, so that's the unique elements question. Right, and so if I give you an array like this, so we'll call the algorithm UE, UE, and if I execute UE on the array, let's say 1, 2, 1, 2, 3, 1, this will return false because it has two copies of 1, right? So the elements of this array are not distinct from one another, right? So this is false. But if I run UE on the array, say 4, 2, 3, 1, this would return true because all the elements in the array are distinct. Okay, so let's just think about kind of a crude brute force approach to this, which turns out it will be fine for this problem. Let's start at element 1 or element 0. And then just check to see if it's distinct from everything else. Okay, and so we'll make sure that we dot our I's and cross our T's and keep track of everything. But we'll just start here, and then we'll check it with this, check it with this, check it with this. And if element 0 is distinct from all following elements, then we'll say we're good for element 0. Now let's move on to element 1. So then we'll check element 1 and we'll see if it's distinct from all the rest, right? So this can be accomplished by a very simple, nested for loop, right? This is not too challenging. So here's some pseudocode that accomplishes this. So algorithm UE, taking as an input an array of n-1 elements, looks like this. So I'll set up a for loop. This outer for loop will be asking, is this element distinct from all following elements? So for I equals 0 to n minus 2, right? Why n minus 2? Well, we don't have to once we've gotten to the end, we don't have to ask if the last element is distinct from the previous ones, right? That's been done. So for I equals 1 or 0 to n minus 2, and then for on the inside here we'll say for j equals what? Equals I plus 1 to again now to n minus 1, right? So if I is 0, then what we need to check is distinctness between, or the difference between element 0 and then element 1, 2, 3, 4, right? So we need to, so the J loop is going to be asking, is going to be chasing down all of the following elements to make sure that they're unique, they're distinct from element I. So basically, if these two are distinct, if I is distinct from J, we'll continue, right? We'll keep looking. Otherwise, we'll return false, right? So if element I equals element J, so if we've found a repetition, then we return false, right? And again, why false? Because we're asking the question, are the elements in this array all distinct from one another? If they aren't, we return false. So if we find equality between two elements, we return false. Otherwise, we just continue the loops. And then at the very end, if we've completed all the loops and haven't returned yet, that means that everything is distinct, so we return true. So this is very Pythonic. It's very Pythonic to have the indentation mean the loop. But if you want to be precise about it, then this is all part of one loop. This is all part of a loop, and then this is all part of a loop. Okay. I'll typically not draw those lines. I'll just trust that you can read indentation and track with your eyes. But anyway, here's the algorithm. All right, so now let's analyze this algorithm a bit. So let's do some analysis. All right, so first, what's our input size? It's the length of the array, right? I've already encoded that with the letter n, so everything is easy. We're good to go. What's the basic operation? Well, the basic operation here, I mean, essentially, it's easy enough to find. It's the thing that happens a lot that takes the most effort, and so it's this thing, right? Really, what we're going to be asking is how many comparisons are we going to make as this algorithm proceeds? And in sorting and in searching and things like that, comparison is usually going to be kind of the basic operation that you care about. So this is comparison. And now what's number 3? Number 3 is set up T of n, right? Set up T of n for the number of basic ops. Okay, as a function of n. So now let's think about what T of n should be. So suppose I give you the following array, right? So let's pause for a moment and think about the following array. So let's do example like this. What happens? What is T of n if I execute the unique elements algorithm on this array? 1, 1, 3, and then it's really, really long, and then it ends in 5. Right. So first, what does this return? Well, we know we have a repeated 1, so this returns false. So we can ask, when did it return false? Well, it returned false when it compared these two. Right. So how many comparisons did it make? It made 1. Okay. So for this call, for this particular input, T of n was 1. Right? And you don't even have to know what n is. I didn't even tell you what n is. You don't even have to know what n is to know that T of n is 1. Okay? So T of n here is just 1. Right? And so here, the running time of the algorithm, in some sense, didn't depend on the size of the input because of the character of the input that I gave the algorithm. Right? So we call this a best case input. All right, so this is best case input. And what do we mean by best case? We mean that that's the shortest running time we can possibly get for this algorithm. And notice that T of n is still a function of n, right? And this is really critical. A lot of time people will say best case, they'll kind of interpret the concept of best case to mean, what size input can I give the algorithm that'll make it fast? That's not what best case means. Best case means what values of input can I give it that make it fast regardless of the size of the input, right? So this is fast. I mean, it terminates in one step regardless of how large the array is. I could give this an array of 20 billion elements, right? And if the first two are the same, it'll return instantly. Right, fast, and the key here is fast regardless of input size. Okay, and that's what best case means. All right. So in the next lecture we'll talk about the other kinds of cases here, but this is the notion of best case.